Hello and welcome to today's lesson on alternators and AC. In today's lesson, we'll start by reminding ourselves how generators use the generator effect to convert mechanical energy into electrical energy. Next, we'll explore the components of a simple alternator and how these come together to produce AC. Finally, we will analyze the various stages of coil rotation and their impact on the induced potential difference, leading to the creation of an AC voltage sine wave. So far, you have learned about the generator effect and the factors affecting the induced potential difference and current. Building on this foundation, we will now delve into alternators to see how they practically apply the generator effect to produce alternating current. This exploration will enhance our broader understanding of electromagnetism and its applications in generating electrical power. Let's get started. To remind you, generators use the generator effect to convert mechanical energy into electrical energy. It's important to understand that there are two main types of generators: alternators and dynamos. Alternators generate alternating current, while dynamos generate direct current. In today's lesson, we will focus on alternators and how they function by rotating a coil within a magnetic field. This rotation is fundamental to how alternators work. Simply put, when the coil rotates within the magnetic field, it cuts through the magnetic field lines, inducing a potential difference across the coil's ends. This is the essence of the generator effect, which we'll now turn to in more detail. A simple alternator consists of a coil, which is folded and rotated using an axle, placed between the poles of magnets. As the coil rotates, it cuts the magnetic field lines. This movement through the magnetic field induces a potential difference or voltage across the coil's ends. When the coil continues to rotate, the direction of the induced potential difference changes every half turn. This change in direction happens because the sides of the coil, after half a turn, begin cutting the magnetic field lines in the opposite direction. This induced potential difference, changing direction, results in an alternating current. To better understand how the induced potential difference creates an alternating current, let's look at the stages of the coil's rotation and how they impact the potential difference. Stage 1 is coil vertical. In the initial stage of the coil's rotation, when it is positioned vertically, the sides of the coil, labeled AB and CD, are oriented such that they move parallel to the magnetic field lines produced by either permanent magnets or electromagnets. At this position, there is no intersection between the coil and the magnetic field lines, meaning that the coil does not cut through these lines. As a result, no induced potential difference occurs, leading to zero voltage. On the graph representing this process, this is reflected as a flat line along the zero voltage axis, demonstrating a moment of electrical inactivity. Stage 2 is coil horizontal. As the coil continues its rotation, it reaches a horizontal position where the sides are now oriented to cut through the magnetic field lines at the greatest angle. This position is critical because it maximizes the rate at which the coil intersects the magnetic field lines. Therefore, at this moment, the alternator generates the maximum induced potential difference, resulting in a positive peak voltage on the graph. This peak represents the highest point of electrical output during the coil's rotation, corresponding to the maximum magnetic flux change through the coil. Stage 3 is coil vertical. Upon completing a half turn, the coil returns to a vertical orientation. The sides AB and CD are again moving parallel to the magnetic field lines, similar to the initial position. This means that, once more, there is no cutting of the field lines occurring. Consequently, the induced potential difference falls back to zero, and the graph reflects this by returning to the horizontal zero voltage axis. This stage underscores the alternating nature of the current being produced, as the electrical output diminishes to nothing after reaching its peak. Stage 4 is coil horizontal, rotating in the opposite direction. As the coil continues to rotate, it again moves into a horizontal position, but this time the sides AB and CD are now cutting through the magnetic field lines in the opposite direction. This reversal is crucial because it indicates that the induced potential difference is still at its maximum, but now in the opposite polarity. As a result, the graph will show a negative peak, signifying a shift in the direction of the induced current. This negative peak illustrates that the current has reversed, a fundamental characteristic of alternating current systems. Throughout these stages, the cyclical nature of the coil's movement in the magnetic field creates a repeating sine wave pattern on the graph of the induced potential difference over time. This sine wave represents the alternating current produced by the alternator, demonstrating how mechanical energy is converted into electrical energy through the principles of electromagnetic induction. Understanding these stages provides insights into the operation of alternators and the fundamental workings of AC electricity generation. In today's lesson, we delved into how the generator effect is used in alternators to generate alternating current. We began by understanding that generators convert mechanical energy into electrical energy through the generator effect. We distinguished between alternators, which produce AC, and dynamos, which produce direct current. Focusing on alternators, we examined their key components, which include a rotating coil within a magnetic field. This rotation cuts through magnetic field lines, inducing a potential difference across the coil's ends. We explored how this induced potential difference changes direction every half turn of the coil, resulting in the generation of an alternating current. We then analyzed the stages of the coil's rotation and their impact on the potential difference, leading to the creation of an AC voltage sine wave. Through this, we saw how the graph of potential difference against time reflects a repeating cycle, illustrating how alternating current is produced. Watch the rest of the GCSE physics course at Sophos Education.